experience. And so Professor John Nichols is a professor in coating technology and director of the National High Temperature Surface Engineering Center at Cranfield University within the School of Aerospace, Transport and Manufacturing. His expertise goes so many areas, but just to mention a few, he's an expert in high temperature nickel alloys, in terms of structural properties and performance, microstructure and damage mechanisms, surface engineering, specifically on oxidation, hot corrosion, and high temperature tribology, coating depositions in techniques with PVD, CVD, electroplating, plasma, heat processes, and design actually of materials and coatings with multi-layer and graded structures. He has published over 280 peer-reviewed research papers, contributed to endless number of presentations, seminars. He has 10 coating patents, and of course he has given numerous keynote presentations. Going back to his history, he was elected professor chair of coating technology in 1991, and he has worked with over 35 leading industrial companies: Rolls-Royce, Siemens, Alstom, etc., right? Just to name a few. Between 2001 and 2004, he established the National High Temperature Surface Engineering Research Center, and he was appointed head of surface science and engineer at Cranfield in 2006. In 2009, he was elected to the Royal Academy of Engineering for his work on low thermal conductivity thermal barrier coatings, and he's also a fellow of the Institute of Materials, Minerals and Mining. And in 2014, he semi-retired, which I'm not sure how that is semi, because you see him working so intensely on several reports that, wow, I can't imagine how it was when he was not semi-retired. He has also strong relations with the European Commission on High Temperature Materials, Coatings for Extreme Environments. He's an IPHRC peer in the Review College, and I'm just really eager to listen to what John is going to tell us today. John, the screen is also yours.
Okay. Thank you. I'll try and share my screen. Okay. Can everybody see the screen?
We see the screen, but we see the other screen. So you need to
move
change into your main screen.
Okay.
It's okay, I think.
So if you have two monitors, right? You need to switch into the other monitor.
Yeah. Okay. So
I think, John, it's okay. We can carry on like that. It's all right.
Are you sure? All right. Else I'd be asking somebody to tell me how to switch between one monitor and the other one.
Try on top, you said display settings. Try to see if you click on top, display settings, maybe it says switch to the other device or something like that. Swap presenting a slideshow. Yes, click that one. Let's see if it works. Yes, there it is.
Okay.
Perfect. All yours.
Okay, thank you very much. And thank you for the invitation to give this webinar. I have to say, I tend to much prefer talking to people face to face than talking to a computer screen. But it's exciting to talk about my research over a webinar with you. So this webinar, glow-in-the-dark surface engineering. What we're looking at is methods of using luminescence. I'll explain as we go through the webinar as a tool to interrogate coating systems within engines at high temperatures. And the idea of using luminescence materials came from discussions I had with Professor Andy Hayes. At that time, Jörg Feast was working for him, and it led to the spin out of a company specifically looking at designing self-diagnostic systems to measure temperatures. We got involved then with working with sensor coating systems and with Jörg Feast, who became managing director of that company back in pre-2012. I use the date 2012 because in 2012, the official Sensor Coating Systems Limited company was formulated, and the work that I'm talking about at Cranfield and the work with Sensor Coating Systems has developed since 12 right up to now. So effectively over 10 years of continuous collaboration, supporting PhD students at Cranfield and joint research projects. So let's move back now and talk about glow in the dark surface engineering, smart coatings for engine diagnostics. I'm going to split the webinar down into two parts. The first part has been a theme of my research for many, many years, and that was to try and develop improved quality thermal barrier coatings. But at that time, I wanted to develop thermal barrier coatings that were self-diagnostic, and working with sensor coating systems allowed us to look at developing what we call self-diagnostic sensor thermal barrier coatings. In other words, building the sensor system into the thermal barrier coating. And you'll see from the webinar that the techniques that are developed don't only have to apply for thermal barrier coatings. They can be applied to many, many different coating systems that we want to build in future. It allows us to develop a system at the moment to measure operating temperatures. And we've done a little bit of work at looking at putting them into tool coatings as well, where they seem to work under that condition as well. But my focus will be on using them in the thermal barrier coating system. So I'm going to be calling this section Intelligent Thermal Barrier Coatings. What I'm going to call it online sensing or online monitoring, which means we're actually monitoring the temperature within an engine when the engine is operating. The second half of the talk, where I say adding a material memory, which was a great innovation, allowed us to now remember those high temperatures and to measure them post-exposure. So I'm going to be calling that offline monitoring. So we're going to talk about using it as part of a monitoring system in a running engine and using it as part of a monitoring system to monitor temperatures that the system has previously seen. So where do we start? Well, we start with a thermal barrier coating system, and if you look in the top right-hand corner, there's a picture there. It's a set of nozzle guide vanes, and each of these nozzle guide vanes have been treated to make them luminescent. And when you illuminate them with a UV light, you can see the three nozzle guide vanes there suddenly are showing red, showing blue, and showing green. Red is luminescence introduced by adding europium. Blue is luminescence introduced by adding dysprosium, and green is luminescence by adding samarium. And we can use the fact that using high energy light, which could be UV or it could be a laser, you can actually trigger the release of this luminescent material, and that gives you a route to actually monitor in situ the performance of these coating systems. So we go from some smart designs of coatings through a choice of smart materials, mainly lanthanides, to make smart functional structures. Can everyone see the slides, or are the little images falling in the way of the slides?
No, I think we can see it, yes.
Okay, thank you. It's just where they are on mine, I keep on having to move them around. In this respect, we went to build smart EB-PVD TBCs. So the area of my main research and where I specialised when I got my appointment as a fellow of the Royal Academy of Engineering was in low thermal conductivity EB-PVD thermal barrier coatings. But what we're now doing is we're modifying the coating by adding a lanthanide into the coating. The lanthanide at a very low percentage, 0.5 to 4 moles %, doesn't actually disrupt the crystal structure of the coating material. It's still tetragonal crystal structure. So it functions as a thermal barrier, but it functions as a thermal barrier plus. And the plus is it is able to interrogate the change in microstructure of that thermal barrier in service through the use of what are called thermographic phosphors. And thermographic phosphors alter the intensity of the light re-emitted depending on their temperature that they're raised to, and this allows us to measure temperature. So for europium and dysprosium, we can measure these temperatures up to around 800 degrees C with a dopant within a standard yttrium stabilized zirconia thermal barrier. If we add dysprosium to it, which is where our first paper in this area was published, we take it up to over 1000 degrees C, 1235 K. And if we modify the thermal barrier by putting an extra surface layer on the thermal barrier, which is a yttrium aluminium garnet, which is a very good receptor for this luminescence, we can take it up to 1700 Kelvin. Similarly, with samarium, you can use in the temperature ranges up to 1000 K. So what do we want in our thermal barrier coating system? I've tried to sort of sketch out what an ideal sensor thermal barrier coating would be like, and I'll take this structure to explain what we're aiming to build into the system. Because it's a thermal barrier, one of the most critical temperatures for us to monitor is the metal substrate temperature. That's where the coating ultimately degrades by oxidation of the bond coat, and that's where final failure of the TBC system will happen. So knowing that bond coat surface temperature is a critical life parameter for thermal barrier coatings. If we coat the top of the TBC, the red color, we can then actually measure the outer surface temperature of the ceramic. And if we have those two temperatures, we can actually calculate the heat flux through the ceramic and therefore the heat load into the engine. And this together gives us a structural integrity monitor method for the coating. If I had my perfect choice, I'd actually put a third layer in the middle of the coating. And the reason I do that is that the microstructure changes all the way through the coating. And this allows me to see how degradation in the outer part of the coating, possibly due to overheat, due to sintering, due to debris infusion into the surface, can alter the behavior, and a measure of the inner part of the coating, which is going to be cooler and will allow me to determine my heat fluxes. And together then, this gives us the ability to do structural integrity monitoring in these thermal barrier coatings. So this first work came out of a PhD student of mine, which is published with Remy Steenbecker being the PhD student and Richard Wellman being the co-author on it. And we deposited a layer of yttria stabilized zirconia with 2 mol% dysprosia added to that stabilized zirconia. Hopefully you can see my cursor moving to where that is. Then built up on top of it through our EBPVD system, a 200 micron yttria stabilized zirconia layer. And in this particular study, the aim was just to monitor the interface temperature of the system. And what you find is that the ceramic is transparent to the luminescence. We end up with a high measure of received luminescence back through the coating, and you can calculate from that luminescence. You pulse the laser at the surface to give a bright, high intensity light charge to it. This triggers electron movement in the dysprosia layers. When those electrons redecay back down, you get what's called a lifetime decay, and you can monitor this lifetime decay to determine what the temperature is. So what we find is as we increase the temperature, we come to a critical point. It's a knee point. Ideally, we want this critical point to be as high a temperature as possible. And then after that, scattering within the crystal structure causes the lifetime decay to decrease, and we can fit this lifetime decay decrease. And from that, knowing the lifetime decay and knowing the temperature it's been exposed to, we can calculate the surface temperature of the component. So using these methods, this shows you the difference between yttrium stabilized zirconia, which allows us to measure up to around 1000 degrees centigrade, just a little under. With the yttrium aluminium garnet layer as a top layer on top of this, it allows us to measure temperatures up to 1700 centigrade. This is particularly difficult to prove. Basically, our highest temperature furnace we had went up to just over 1500 centigrade, but we have recently done some work with NASA where we've used the burner rig and we've been able to measure temperatures up to 1650 centigrade. So the system has a capability of measuring temperatures up to 1700 degrees centigrade with a precision of plus or minus 5 degrees centigrade. Our excitement comes when we try to be a little bit more complicated in our manufacture of the thermal barrier coatings. So we take a TBC bond coat, we deposit a first layer. This is a layer, say, with dysprosium in it. We now deposit a standard layer on top of it. And we then deposit a layer with thulmia in it. With these 2 phosphors, we're now able to measure 2 temperatures. We use the same UV excitation wavelength, but it excites one frequency from that top layer, phosphor B, and 1 frequency from phosphor A. And we can simultaneously monitor both of those because the TBC is transparent, and therefore we get a temperature measuring the interface, which can measure up to around 1000 degrees centigrade. And we have another temperature that can measure the surface that we have validated up to 1300 degrees centigrade. But that was the maximum temperature of our furnace when we did this test. This then, for the first time, allowed you to measure heat flux. Because knowing the surface temperature knowing the interface temperature and knowing the thermal conductivity of the ceramic in between, you can calculate the heat load needed into the system, and it provides an online monitoring tool for performance evaluation within your engine. So, how do we prove it? Well, SES purchased a Rolls-Royce Viper engine. It's quite an old engine, so it wasn't that expensive, but it was still custom purchased for these tests. It was installed in Cranfield in our engine test facility, and it was operated at Cranfield. And now, if you look then on the right-hand window, you can see a green spot of a green laser. And what we're actually doing now is pulsing the laser between the nozzle guide vanes at a set of blades that are passing behind the back of it. And with the blades running in the engine, we have 140 microseconds to take a temperature measurement. And you can keep on pulsing this laser between the nozzle guide vanes. We developed special instrumentation to feed the laser light in through optic fibers. And from the rate of decay of this luminescent line with temperature, you can calculate this the temperature and hence the performance of the engine. So this is one of the coated blades. It's not a cooled blade, but we are able to coat it with TBC. But the important thing I want to show you is the graph on the right-hand side. The engine was instrumented, so we could measure with a gas phase thermocouple upstream of the blades. We could measure with an exhaust thermocouple downstream of the blades, and we could measure the speed of the engine. And as you step the speed of the engine up, you do that by raising the temperature in the combustor and therefore the gas temperature into the engine. And you can see the step cycles of the temperature raising and then decreasing again on the other side. You can similarly see the exhaust temperature measured with thermocouples. And the purple line in the middle is the results of this luminescence sensing system as we stepwise increase the engine speed from 1,000 revolutions per minute up to 1,300 revolutions per minute and back down again. So the TBC sensor coating exactly measures the blade temperature in this test during this load cycle test on an engine condition, and is in measuring temperatures on this rather old engine up to around 900 centigrade. So for us now, this was an exciting part of the technology. We had a method of measuring temperature. We had a method of measuring heat flux. I was very interested in could we use this thermographic phosphor to give us other structural health monitoring information. The lifetime of a TBC is dictated by either the interfacial oxidation or by a change in phase within the TBC, which forms a monoclinic form of the TBC. So I wanted to see whether we could monitor phase change. And I was also interested in whether we could monitor ballistic damage and sporulation. So the follow-on programs from this looked at how these TBC systems in situ with the luminescent dopant, these lanthanides as phosphors, would be able to monitor structural health and erosion performance of the engine system. So aging and phase change. If you take a spectral response of these luminescent signals, you get peaks of luminescence depending on the crystal structure, and these peaks relate to where, in this case, the dysprosium sits in the yttrium sites of the yttrium stabilized zirconia. So the dysprosia substitutes for the yttrium. Depending on which yttrium site they take, you end up seeing a number of spectrum peaks. And if you notice, there's a spectrum peak here that seems to be growing in size with temperature. And that spectrum peak, that separate side peak, is due to the formation of monoclinic phase during the aging of this TBC in an engine service or in our laboratory furnaces. So we heat treated the TBC at 1500 centigrade, and we aged it for various times, 100 hours through to 1100 hours. And we monitored how the side peak changes in that luminescence response. And when you take that luminescent signal height, it's actually a measure of the intensity. And what we do is we ratio the intensity of that peak to one of the neighboring peaks. And if you see on the graph, it's 585, which is this peak. It is this peak, which we take as a reference, divided by 580, which is this peak that is growing in size. And this ratio here allows us to generate a calibration curve, which from this intensity ratio, which relates to the percentage of monoclinic growing in the TBC coating. So by using this laser luminescence method, you can in situ in a coating see these changes in phase, relate it to exposure and time dependence, and therefore relate it to the ultimate concentration of monoclinic in the ceramic, and this relates to final TBC coating failure. As for erosion, this became a very interesting challenge for us. Effectively, if you look in this top disk, you see in the, a TBC coated system. You'll see there is a crater forming in it, and that crater is where we've been eroding it with high velocity alumina particles, effectively boring down through the TBC and the ceramic. But the coating is not just a single layer coating, it actually consists of 3 layers. We have a YSC, yttrium stabilized zirconia TBC. We overcoat it with 30 microns of dysprosia doped yttrium stabilized zirconia, and then we've overcoated it with another 30 microns of europium doped yttrium stabilized zirconia. We can then, using luminescence imaging and UV light, image through the ceramic to these europium and dysprosium layers, and therefore image how much of the europium exists, the red, how much of the dysprosium doped layer exists, the blue, and how much of the YSC with neither of those dopants in it exists. And that allows us to generate a contour map of the mechanical damage on the coating, and we can calibrate the intensity ratios of these signals to measure depth. So in this particular case, it's dark blue here, we're about 110 microns, and on the top we're about 150 microns and or 140 microns, and that's probably the surface thickness of our original coating that we put down. It was notionally going to be 150 microns. So it clearly shows by using more than one dopant in these TBC systems, we can structurally health monitor erosion within the TBC. at this stage, we had a very good monitoring system. It could be used in situ within an engine, but it couldn't really be used in situ within a flying engine. And the reason is you have to take a payload of high intensity laser into your engine and have it operating in a plane. But we were able later to validate it in industrial gas turbines, and I'll show you some of that in the next few slides. But at this sort of time of looking at the structural health monitoring, in discussions, we were saying what it would be really nice to do is to be able to expose this TBC in the engine. And at the next time the engine shut down, scan the component in its cold state rather than in its hot state, and see if any damages has happened in the coating, hence the structural health monitoring. But could it be possible by the correct choice of material design actually to remember the temperature that the component had seen when it was running hot? And this was a huge challenge. The net outcome of it is what we call a thermal history coating. You'll find it's one of my patents. It's a patent along with Jörg Feist, the managing director of Sensor Coating Systems. And effectively, what we found is that if we took a sample, it's now of a layered coating on top of a TBC, and we held it for, say, 10 minutes at peak temperature. And unfortunately, the composition of that layered coating is commercial. So you would have to approach Sensor Coating Systems and ask them to get some of the parts coated for you, because it's their proprietary knowledge. But we have a coated layer on top of a TBC or on top of an oxidized substrate. You heat treat it at various temperatures, hold it at temperature for 10 minutes, and then you measure the lifetime decay afterwards when it's cooled down. And what you find is you can generate a calibration curve that relates the lifetime decay to the temperature the material is seen when running and operating hot. And we can do this with a precision of about plus or minus 10 degrees C. So this outer coating layer is compatible with TBCs, is designed to store a permanent phase change depending on the peak surface temperature that's operating. Effectively, in this particular coating, we can put it down by either a thermal spray method by plasma spraying, or we can put it down by a sol gel method. And we actually, in so doing, we produce a material that is partially amorphous. So you have your lanthanide ions, your europium or your dysprosium, trapped in a partially amorphous structure. You can then excite this with a laser, something in the UV or blue, and you can detect the emissions from the lanthanide and use those to actually monitor the behavior. When you trigger the luminescence decays with time. That's the curve on the right-hand side here. And what you find is this time decay, the rate of time decay that you get varies with the service condition, the service temperature, and the aging of that TBC layer or ceramic layer that you've put the luminescent ion into. It follows a classical exponential decay, and you can model this. So what in actual happens in this coating system is we start amorphous, we then form networks and small crystallites within the system, and slowly those crystallites grow till the coating becomes fully crystalline. And if you freeze it anywhere in this route, depending on temperature and time, you actually get a measure of the temperature and the time. And this particular coating system's designed to have a non-reversible material change, and this provides us the material memory. So one that we have published is we took this route for the YAG layer that we put on top of the TBC, so YAG dysprosia. And if you look at the wavelength curve on the left-hand side now, you can see an amorphous peak when it's aged at 310. You can see a different shape amorphous peak as we age at 865, and now you're starting to see some crystalline peaks coming up. If we age it at 904, you start to see quite a number of the crystalline peaks in place. And from this rate of crystallinity, we calculate this decay constant, which we measure using the luminescence, and you can plot that decay constant against temperature, and it allows you to produce a calibration curve. So when we use this as a temperature sensor, we pre-calibrate the coating systems and then use the calibration curve to measure the temperature within engines. So I'm just looking at the time. I'm going to go over a little bit. I'm sorry, people. But here's some examples. I'll take you through the examples. This was the original Combustor running at Cranfield when we first tested this. You can see the cooling patterns from the cooling hole, and you can see local hotspots coming up in the coating, illustrated by the luminescence measurement systems. On a commercial combustor system, you can identify here the cooling passages in this combustor system, and you see the blue colorations where the ceramic or the coating system is cooler, and from this you can actually produce contour plots of the hot spots within the combustor, and you can actually measure the temperatures accurately within these hot spots. I'm not allowed in this condition to say what these temperatures are, but I have other examples where the sponsors have agreed that I can release the temperatures to show, but it shows you the ability to complex map thermal profiles within a combustor post-exposure outside the engine after it has been heated and operated within the engine. We were lucky to be able to work on a Siemens engine and get into the DCOT power station, and we were able to instrument up a thermal barrier coated combustor tile. It sits in this position, and you can see post-exposure, and this was in a service interval of 4,000 hours, where the cooling hole is, and the blue area of where the cooling air has passed over that combustor, cooling that part of the ceramic, with the upstream part of the ceramic seeing higher temperatures because it's above that cooling air injection port within the Siemens engine. So the message from here is this is a really durable way of measuring in situ the temperature capability of various engines, and that you can do these measurements post-exposure within the engine. With that background, sensor coating systems and ourselves, and I'm on the board of directors of sensor coating systems as well, look to commercialize this thermal history coating thermal mapping method. And to do that, we had to improve our precision of measurement, and we did that by introducing a monitoring system based on optic fiber and laser, operated by a robot, so that we could take multiple temperature measurement points around a component, generating what's called a bubble plot, which you can see on the right-hand side here. Effectively, the procedure now gives a unique method of profiling temperature. We start off with our sensor ceramic. It can either be paint sprayed, so it can be a paint coating for low temperature operations, or it can be plasma sprayed down for high temperature operations to coat the component. The component can then be operated at high temperatures. Post running the engine, we receive the component back at SCS Limited, and using this pulse laser, we take measurements. Each measurement's about a 1 millimeter square area that's interrogated, and you can take measurements on the blade surface, on the platforms, and on any complex shaped part, and generate a digital temperature map of the component surface. Spot size in that 1 millimeter is about a 0.5 millimeter. We can take around 300 points in about 2.5 hours by automatically stepping round the part and rotating part in the robot. So you generate a bubble plot. You can see the bubble plot on the blade, and as a result of the bubble plot, you can produce a contour map, and the image that's rotating is that contour map onto a CAD image of the blade surface, which allows you to map out with high precision, typically plus or minus 15 degrees centigrade, the temperature anywhere on that surface post-exposure in the engine. So the coating thickness is about 30 microns. Our resolution is about 1 millimeter square. If we use the paints, we can measure up to 900 degrees centigrade. If we use it in a plasma spray coating, we can get up to 1650. And it's now been exposed in engine conditions up to 4,500 hours in a demonstrator. And our precision, we like to think 5 to 10 degrees centigrade, but often in arduous conditions, it may be a little larger than that, and it may be 15 degrees centigrade. Taking a few examples to show you this, and I know I want to give you a chance to ask me some questions. This is a temperature profile. The exact temperatures in this one, we're not allowed to publish, but the red dots are temperatures made with a thermocouple that were embedded in the component surface. The blue dots are the temperatures measured with a thermal history paint in this particular application, THP, and this allowed the engine operator in this case to generate a contour plot of their thermal image of their operation, much more precise than they'd ever been able to measure by other thermal imaging methods within the engine. And that was published in Turbo Expo in 2017. Another example on a combustor can, which has got micro cooling holes all the way across it. You could actually map the temperature surface, and this allowed us to give a go, no-go CAD plan, 2D of the surface of where the likely hotspots and cool areas were on their cooling patterns that they've planned into this combustor can, allowing high resolution analytics of these combustor components. And this is almost now the last slide. This was work we undertook with NASA. It's a ceramic matrix composite that they were running in their burner rig. They operated it, and we were able to post-exposure measure the temperatures using the bubble plot. You can clearly see the reds in the hot zone. You can see the warm areas in the greens to blues, and you see the blue areas where it's cooler. If you take a vertical line through that hot spot along that leading edge, you can actually plot the temperature profile across that leading edge, showing that we were up to around 1470 centigrade, and the red crosses on that plot are pyrometer measurements taken on that same surface, which validates and calibrates that our thermal history coating was precisely able to measure the temperatures. So I'm going to come to a conclusion here. I'd like to introduce the sensor coating systems team. Jörg Feist is the managing director. Sylvia is the technical director. I'm on the board of directors. It's a new spin-out company. It's been running since 2012. We have about 24 people operating in the company for us, aimed at precision temperature measurements using luminescence in many industrial applications operating hot, with temperatures from 300 degrees centigrade to 1600 centigrade. So I can summarize and finish. Thermal history coatings, the use of luminescence lasers provides a novel coating system for in situ temperature measurement of component surfaces, and therefore prediction of life of components. The temperatures, if we use it with the memory materials, can be measured post-exposure, allowing you to produce rapid digitized images to optimize your future manufacture for future low emissions engines. And at that point, I'll say thank you all very much for listening, and I'll answer any questions.
Thank you very much, John. It's impressive, and I think we should clap now for your great presentation. So, is there any question from the audience? Maybe I start with a question, and if you have any question, you can just write on the chat. So the first question I do have, John, is luminescence is coming from a very small scale, right? What happens with mesoscales? Is there any interference when you have, structures with that process?
Yes. So effectively, the process is looking at the lanthanide, the europium or the dysprosium ion, because it's in an oxide system. It's looking at its local environment. So anything that changes that local environment can change the signal. So effectively, that's why I can measure phase change, because as we go from tetragonal to monoclinic, I alter these lattice spacings of the atoms. Those lattice spacings of the atoms change the local environment around the europium atom, and therefore the europium atom luminescent signal changes. So it's very much sensitive to what happens at that nano scale within the system. As we then build it up to a component, we bring in grain boundaries, phase boundaries, defects, and they all modify the performance, and therefore effectively what we're comparing is methods by which the energy is being dissipated that was excited by the lasers to start with. Some of those methods can be scattering in boundaries and grain boundaries. Others is by optical decay and re-emission of the light, which is what we detect. So you trade off of both of these. So can you say exactly which defects do what? That's an area we're still learning. But what you know is, because we measure it and average over a global area of 0.5 millimeter diameter, we're actually measuring the average performance of all those defects that we get in that sampling volume.
Mm-hmm.
And then we can calibrate that average performance in that sampling volume against temperature, which allows us to map temperature. So for what we need from an industrial point of view, there's a bit of a trade-off about what size spot do you really want for some of the measurements you need. But at the moment, we're offering 3,000 data points on the surface of a turbine blade.
Mm-hmm.
Where previously you might have had 3 or 4 thermocouples on the blade, roughly, to work out where it was. And if it was a rotating blade, you'd painted it with a thermal paint, and the thermal paint only could tell you the difference between, say, 200 degrees C and 300 degrees C. So there's room for more improvements in it, no doubt. But the principle of using these luminescence at the atomic level to interrogate material surfaces, I think is very exciting as a monitoring tool, not only in TBCs, but in wear surfaces. We could measure the temperature of a contacting point as a tool went across a component surface, for instance, by using these sorts of laser luminescence methods.
So what you're saying is it's not only the chemistry, but also the microstructure you have in there, that they work together.
In the thermal history coating, we're effectively looking at a TTT diagram, time temperature transformation.
Mm-hmm.
It's not one transformation, it's amorphous to crystalline 1 to crystalline 2, and we're mapping a series of ongoing transformations that allow us to deconvolute the temperature.
That makes sense. There's a question from the audience, and it says, any effects on the surface or bulk properties? Do these changes really matter?
Okay, there are surface effects for the same reason we just talked about. So if something deposits on the surface that reacts with the surface, it will change that surface layer.
Mm-hmm.
But bear in mind, the laser light can penetrate into the TBC. So in actual fact, what we would see is we'd see a signal from within the TBC if we put the additional layers inside, as well as the surface layer. So it might be a method of detecting whether you've got any surface damage.
Mm-hmm.
So yeah, it's absolutely true. If you change that surface chemistry, then we can partly overcome it in that we can take the material and put it through a simulated exposure similar to what you would expect in an engine. So we do that, we would expose it in, for instance, combustion gases, if we were looking at it in a combustion chamber or something like that. So that we get similar sorts of chemistry changes in the sensing system, but it is sensitive to potential surface changes, but it does penetrate and measure within the surface.
Excellent. And there's a follow-up question. Actually, there are a few questions here, but a follow-up is, what about the TGO growth rate during the operation of the TBC system? Is that changed?
The TGO rate, is, as far as we have measured, is not modified by the small amount of dysprosia that we put into the standard YSC.
Mm-hmm.
It's only 0.5 to 2 atomic percent, and in previous work that I've done, we were adding of the order of 2 to 3 atomic percent lanthanized to produce low thermal conductivity ceramics. So potentially on thermal properties, it's a benefit. But what we do know is, yes, clearly with you, as you age it, the oxide thickens, and you are able to monitor then the changes in the interface temperature when you're under a gradient. So it's a much more precise tool for determining the rate of thickening of the oxide and therefore the ultimate life of the TPC component.
Mm-hmm. Excellent. So there are more questions coming. This one is this sensor coating part of the thermal barrier? Is this underneath the barrier coating?
Okay. If it's the one for in situ monitoring, so what I call online, it's an integral part of the thermal barrier.
Mm-hmm.
So it's doped into the thermal barrier on the first layer that goes down on the TPC, and if we wanted to make the gradient structure, it would be doped in the surface layer of the thermal barrier at the same time, and that would allow us to get the 2 measurement points we need to calculate heat flux. So that in that case, it's an integral part of that thermal barrier. For the thermal history variant, the one that we can measure afterwards, it doesn't have to be an integral part of a thermal barrier, but we have experience of using it as part of the thermal barrier, and it isn't a detriment.
Mm-hmm. Excellent. So there are 3 more questions. I'm gonna summarize those quickly. The first one is, how are you measuring the temperature inside the high temperature section, and if that measurement is affecting the temperature actually?
Okay. So when we run it and measure it in a high-tech operating engine, clearly there is radiation from that inside the combustor on the system. So that gives a noise effect that one would anticipate. But bear in mind, what we're doing is we're pulsing the laser. So we can time frame these pulses such that they pass between the nozzle guide vanes to hit the blades. But that means we've got a periodic function pulsed laser as an input signal, and we can then use that to gate the information coming back from the luminescence. So we effectively gate the signal to reduce the noise. And the luminescent signal that comes back is very much one wavelength, pre-tuned by what the luminescence system we chose, whether it's dysprosia or Europia. And so effectively, we end up still getting quite a good signal to noise ratio out of the readings. So I don't believe the local combustion effects and radiation influences the readings we make.
Interesting.
Post-exposure, the ones for the thermal history, clearly we move away from any problems within the combustor. You gain the benefit of being able to take multiple readings over the whole surface and to thermal map the whole of the component.
Mm-hmm. That's very clever and interesting how deeply the analysis on not affecting the temperature actually in the turbine. Okay, so there are a couple more questions. So a follow-up on the TGO is, which are the phases formed in the TGO after operation, and did you observe any alpha alumina with globular shapes?
Can you say those again?
Yes, yeah. The phases in the TGO.
Yeah.
And then if there is any alpha alumina with globular phase, so globular shape.
Okay. This is really moving outside of the work with sensor coating systems, but from my experience, when we make these coatings, we deposit them within our coater at temperatures over 1000 centigrade. So the TGO initially forms as alpha alumina. It effectively stays as alpha alumina right through almost to the failure point. What we do though find is because of the outward aluminium transport, you get voids forming underneath the alpha alumina, which ends up being the root path of where the failures go. But we don't really see many other non-alpha alumina oxides forming in a TPC that I would have made.
Good. Okay. I hope that answered the question. And then the last question, it's going to be two, one from my side and one from the other side. Have you looked at the mechanical properties of this? And on the other side, have you looked at the role of stress on this, properties to tell you the temperature?
Okay. Both very good questions. I can understand why they're raised. When we're using it as an online monitor and it's part of the TPC system, we deliberately put the TPC system down with a columnar microstructure because it's strain tolerant, and the coating doesn't block those vertical column boundaries. So it actually grows on top of the TPC or is integrated into the top of the TPC. It still has its strain tolerant columnar microstructure, so I don't see the stress problem within that particular coating system. If we look at it in terms of the coating as a thermal history coating, we deliberately deposit nowadays a thermal barrier coating layer on prior to putting the temperature sensor coating layer on, albeit only very thin. This deconvolutes any surface oxides that may form, and therefore chromia or nickels that may form from interacting with the temperature sensing paint. And it also means that the temperature sensing paint now only has to match the strain in the ceramic TPC, and there are similar ceramic materials, so the strain difference at the moment doesn't generate sporulation of the coating.
Okay, so structurally, it's not different from other coatings.
Yeah, structurally, it's not different from existing coatings. The excitement of the work with NASA is that the NASA was on a CMC, ceramic matrix composite, which is protected by a silica-based layer, an environmental barrier. Mm-hmm. This coating was therefore put on top of the environmental barrier. It still managed to go up to 1,550 centigrade in their burner rig, and it was cooled down from their burner rig, and we didn't lose any coating.
And what about the luminescence and effect and stress or strain? Is that affected?
This is a very exciting one. There is very little data on it at the moment. That doesn't mean that we shouldn't do it. People have looked at it with other wavelengths, so interrogating with terahertz. Mm-hmm. I think stress could alter the luminescence, but relative to temperature, it's a minor effect, but it is potentially a detectable effect. If I look to the future, I have an ambition of being able to design a coating that can measure temperature and strain, not stress. You measure local surface changes in lattice spacing. So I would like to take this work further and develop a system to in situ measure both stress and strain. Mm-hmm. I think it's possible, but that we have to look at for the future. I can't do it at the moment.
Very, very exciting. And I think I don't see any other question. I think this is a great way of concluding this talk with this pathway to the future in which we hopefully will be able to see strain and temperature from one coating, which is, it really sounds like science fiction. So unless there's any other final question, I really want to thank John for his participation today, for this fantastic presentation. This is gonna be online on YouTube channel, and I wish you a good afternoon to everyone. And once more, thanks, John.
Thank you, everybody.
All right. So with John, and thank you so much, and keep posted on our YouTube channel. There are other great seminars for you